¿Listo? No sale. Okay, so hello everyone to a new session of our quantum statistical physics seminar. Today we have a guest, which is Victor Domínguez-Rocha, who is a research professor from UAM, which is the Metropolitan Autonomous University in Mexico City, and he will talk about exponential points in an elastic system. He received his doctoral degree also from UAM, and has made postdoctoral tenures at Meritorious Autonomous University of Puebla, National Autonomous University of Mexico, and the Wesleyan University in the United States. Nowadays, his research lines are in experimental physics, acoustic, wave transport, and others. At the end of the presentation, Victor will answer the questions that you will leave us in YouTube. And as well, thank you very much for coming, and the stage is yours.
Thank you very much, Adrian, for the kind invitation. Just a little comment is that I am not a researcher professor in the UAM Iztapalapa, not yet. I'm still in the postdoctoral stage, and as all of the postdocs are looking for a job, so thank you very much. As Adrian comment, I made my PhD in UAM Iztapalapa with Moises Martinez Mares, and I developed some theoretical studies. So basically, my thesis was in electronic transport. But you know, life is quite interesting, so it moves me to the experimental part, which is very nice because I have a bigger view of physics. And so I moved to Puebla, then I moved to Cuernavaca with Rafael Mendez, and I performed my first experiments there. And then they opened a postdoctoral position in Wesleyan University with Sampicos Cotos. So I applied and I won that position. And this is why I am gonna talk to you about exceptional points in an elastic system. So first of all, Wesleyan University is in. Let me use my laser. Wesleyan University is in the Connecticut state, which is between New York state and Massachusetts. So it's very far at the north, and this is more or less where the logo, let's say, the logo of the university. So this is New York. Here is New York. Here is Boston. Here is Hartford, the capital of Connecticut. And this university is in Middletown. It's a very nice university, especially from arts. It's the most prestigious university of arts in the US, but also has some different departments like physics, chemistry, biology, astronomy. So this is why I was there in Middletown. Let me introduce my colleagues for this paper. Professor Sampicos Cotos from Wesleyan, and also Professor Ellis, also in Wesleyan, and Tevamaran Ramatasan from Wisconsin-Madison University. And this is how they look like. So this guy is Sampicos, and all of these guys are his group. This guy over here is Fred Ellis, a very, very nice experimentalist. And this guy is Tevamaran, very nice guy too. I guess he's engineer, I guess. But please don't believe me about it. So this is the outline of the talk. I'm gonna talk very briefly about exceptional points. I'm gonna give you just an approach. I will try to explain what is an exceptional point. After that, I'm gonna uh, I'm gonna show you some console simulations, and I call it a spaghetti of modes. You will see why. And after that, I'm gonna talk about the experiment, and finally, I'm going to conclude. So when we think about experiments and the theory, uh, I really like this image, because from one side you have the theory, and on the other side you have the experiment. And it will be very, very nice to have a very beautiful bridge like this one, so you can cross between the theory and the experiment, especially when you have help from console, a numeric simulation. So it should be easier to go from one to another. But life is more complicated, and you will see why. So let me start with the theory, then I'm going to move to console, and then I'm going to finish with the experiment. So the exceptional points. What is an exceptional point? I'm going to talk very superficially, let's say, about what is an exceptional point. And this idea is going to take me to a PT system. A PT system is something like this. So let's imagine that we have two balls, two masses, and they you have the system with three springs. Let's say two of them with K knob, and the inner one is just K. But the point here is that you will add, let's say, something like friction, right? So this is the minus gamma. We are very used to see this parameter in classical mechanics. And let me think more beyond the imagination, that you can, instead of have a friction, you have something that is going to increase the motion of the mass every time you move it a little bit, right? So I'm gonna apply a parity operation. The parity operation is going to interchange the positions of the two masses, as you can see here. So the red and the green are in the opposite positions, and then I'm going to apply a time operation. I'm going to apply the T operator. So this is going to interchange the signs of the friction. So I let me think that the friction is something like a loss, and the opposite is going to be a gain, right? So when you apply these two operators, you are going to come back to the original system. So this is called a PT system. It's a system which, after these two operations, you are going to recover the original system. So this is basically what is a PT system. So now let me move to um, kindergarten quantum mechanics, and let me draw this potential. So you have two infinite walls, so it's an infinite well, and you will have a particle in the well, right, in the infinite well. So you have here your ground state and the first excited mode, and you will have, obviously, the of the spectra of the energy right over here, something like that. But when you take the height of the potential, instead of being infinite, let me take it down. So the well is gonna be finite. So the wave function can penetrate to through the walls, right? And this is for the more or less for the first excited mode. And let me take two of these systems, two independent systems, which are an infinite distance from one to another, and they are going to have, if the wells are equal, the spectrum of the energy is going to be exactly the same, right? But what happened if you put one of the wells next to the other? What is going to happen is that the nature doesn't like degeneracies, so you are going to find a splitting of the eigenenergies. So this dashed line is the position of the original energy, and these two energies are going to be the energies from the, let's say, from the left and of the right well, right? So you have a natural splitting. Actually, actually, you will have two different modes. One of the modes is going to be symmetric, the red one, and the other one is going to be anti-symmetric. So this, you're going to have two different energies for the two different modes, right? So the question that I can do here is, what can I do to make both eigenenergies to touch each other, right? Because they are splitted. So the question is, it is possible? Can I do something to create this degeneracy again? And the question is that yes, I can do that, and let me show you how. Let me add to the potential a complex part, let's say plus I gamma and minus I gamma. So this is the parameter that I'm going to change symmetrically. So it's the same parameter for the two wells. And if I write the matrix derived from the Hamiltonian, or something very simple, I'm going to have something like this. So in this case, the x is gonna play the role of the energy. So I have the plus and minus, the gain and the losses of this parameter, and the coupling between the two wells. The two scatterers are going to be coupled with a strength, which I will call it C. So if you find the solution of this, and you plot it as a function of the gamma parameter, you are going to find something like this. This is going to be the real part of the, let's say, the energy, and the imaginary part. So when gamma is exactly zero, you have the natural splitting of the system, of the both of eigenmodes, right? But if you start increasing this gamma parameter, they are going to coalesce at a certain point, which is called exceptional point. So this is basically what very simple. This is a very simple idea. This is a very simple way to show to 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 try to explain what is an exceptional point. And after this point, both of the eigenmodes are going to become one, right? And the imaginary part is going to be splitted. Actually, one of the modes is going to be the complex conjugate of the other one. So this is the symmetric case when you have gain and losses, and they are equally syntonized, right? But you have another option in order to find an exceptional point. Let me study this case of loss and more loss. So let me add, instead of have gain, I'm going to add a natural, let's say, a natural loss to the system. Let me call it minus gamma now. And in the other scatterer, I'm going to play. Also, I'm going to add this natural loss. Let me call it like that. And I'm going to add this gamma parameter, which is the one that I will be able to syntonize. So in order to see what is going to happen with both eigenenergies, and this is what I'm going to find. Again, I'm going to find an exceptional point exactly at the same position as the symmetric case, balanced case. I mean, with the gain and losses, right? But the imaginary part of the energy is not going to be one is not going to be the complex conjugate of the other one. So it is going to be positive in always, and this is how it's going to look like. So now we have the idea of what an exceptional point is, right? It's very simple. There's a lot of papers and books, because the idea of the exceptional points arises, I guess, in the 50s with Cato, and it was recovered at the 90s, and too many people has been working in exceptional points and what is going to happen with this and different areas of physics. So the question for us at this point is, what is the simplest system that we can study in elasticity that can show an exceptional point? So the the thing is that it has been proved in many situations, like for example in electronics or in optics, that they were able to perform and to prove an exceptional point. But the elasticity is complex per se, because as you can see in around your places, everything is a continuous. So if you hit, for example, the wall or the table or something, everything is going to move in all of the directions. This is no longer a one-dimensional system. Elasticity deals with three-dimensional systems. There are certain approximations where you can work with the one-dimensional, quasi-one-dimensional elasticity theory, or quasi-two-dimensional systems, something like that. You are able to play, but elasticity itself is very complex. Very complex. Actually, it's a tensor theory, so everything is mixed, right? So in order to build a system who is going to show an exceptional point, I will use a tool, a very nice tool, which is called COMSOL. COMSOL. And this is a very nice program which is going to mesh all of the system, and is going to solve numerically the solution of the geometry that you're giving to it. So I will explain why an spaghetti of modes. And the question here is, what is going to play the role of a scatterer? If you remember, I have this quantum system of two wells, and this can play the role of scatters. But in elasticity, what is going to play this role? So the most simple thing that we thought is to take a brief trip to 1D elasticity. So in the one-dimensional approximation, you have three different modes: the compressions, which are over here, the torsions, and the bendings. So this for a parallelepiped. And as you can see, I have the three different modes: the compressions, the torsions, and the bendings. And these are the equations who describe these three different modes. So as you can see, I have the bending modes are four-order differential equations. So we don't like, I mean, it is enough complex to work with elasticity. So I am able to make my life simpler. So I don't want to deal with the bending modes, right? So I have two different guys who can work the role of the of the scatterers. So I have compressions and torsions. What you are seeing is just a simulation of how the is going to be displaced. Of course, this is an exaggeration, and the blue means no motion, and the red means maximum motion, right? Maximum displacement. So I have these two guys, and I'm gonna choose the torsions. I'm gonna explain further why we chose the torsional modes. So here, so these are going to be our proof guys. So I need two of them because this is one, and this is going to be one scatterer, but we need two of them, right? And the question here is how they are going to be coupled. What is going to happen when I couple these two guys? Exactly as the quantum case, if you couple two scatters, the eigenenergy, the energies of the system, in this case is going to be the frequency, the frequency is going to be splitted, and you are going to have two different eigenmodes, the symmetric case and the anti-symmetric case. Like in this case, you can see that they are twisting in the same direction, so I will call it that they are twisting together, which is the symmetric case, and in the opposite case, where the motion is in the opposite direction, right? So the question remains how you are going to couple these two guys experimentally, also numerically. I mean, numerically is simpler, but it's more simple to couple everything you want numerically because you don't have to build it. But our purpose was to perform the experiment. So let's say that I had an epiphany, and that this is the system that I want to study. As you can see here, you have the two pillars with the dimensions, with the correct dimensions, and they are coupled through a plate with, let's say, these dimensions of the length and of the depth. As I told you, to reach to this point, that this is the best system, the simplest system to study, it took too long, too much time. So let me show you now what is going to happen with the spectrum of the eigenenergies when I change just the width of this plate. I'm going to change just one parameter. What is going to happen is something like this. This is why I call it a spaghetti of modes. All of these points, which in principle are continuous lines, but depends on your step on the simulation, represent all of the modes of the whole system. So as you can see here, is more complex than just a one-dimensional system. I mean, I love one-dimensional systems. My PhD thesis was about a one-dimensional system, but the reality is hitting you in the face. So is more complex. So let me show you here the red lines. In principle, should be lines. Are the two torsional modes of the pillars. So they are coupled, so they are going to be splitted, right? And all of the other guys, all of the other modes are the modes of the plate. So you have to find a place. I mean, and as a function of the width of the system, you have to find a place where you can study the system, which in order to be far away from the different modes, because they can interfere with your torsional modes, and you don't want that. So let me do a close up about around this this little square, and this is what is going to happen. Again, these two guys are the torsional modes of the system of the killers, and all of the other lines which are crossing or you have avoiding crossings are going to be the modes of the plate. Okay, these two blue lines are just I added by hand just to try to find 500 hertz difference between the torsional modes and the other ones. So it will be very, very nice to have isolated modes, but in the reality it is not so simple. Let me show you a little bit how. For an example, I have these two torsional modes, as you can see here. So is the symmetric case is the lower one, and the anti-symmetric case is the upper one. And this guy, which is here at this point, is exactly this mode. So as you can see, there's a big motion of the whole system. And if you look carefully, let me try to do a zoom over here. Oops. As you can see, the wires over here. I don't know if you can see my cursor, my hand over here.
Yes, that is it.
Okay, thank you very much. So the wires, the black wires, represent the equilibrium of the system. And again, the blue is the no motion, and the red is the biggest displacement of the system. So for this case, for this for this mode, as you can see, there's something that it looks like a compression. So this is why we chose the torsional modes, because they are very difficult to couple with the modes of the plate, right? If your plate start moving something like this, the compressions are going to be promoted into the pillars. So it is going to be easier to have a mode that you don't want, right? So that is why we chose the sorry about this. So this is why we chose the torsions instead of just the compressions, or worse, the bendings, because they are more complex. And we don't life again life is enough complex, and we don't want to make our life more complicated. But not at all, because as a physicist, as scientists, we really like to suffer a lot in order to understand, of course. So this is going to be the system that I'm going to study. Actually, I can tell you the spoiler that 12.8 centimeters is going to be the width of the system that I'm going to study. So actually, it's going to be something like this, the width. So we have two different modes of the plate, enough, very near of the torsional modes, but enough far away to be worried about it. As you can see, in lower frequencies, they are going to appear, which is obvious, but they are going to be more far away. So this is exactly the parameters that we are going to study. But suffering is never enough. So let me do the system more complex. Let me add an indent at the middle of the system. So I'm going to break the mirror symmetry in this direction, not in this direction, but just in one of them. And let me study again what is going to happen with these torsional modes, super torsional modes. No, it's not so super torsional modes, just the torsional modes, the couple torsional modes, the symmetric and the anti-symmetric case. So as a function of the radius of the hole in the plate, it's going to happen something like this. So obviously, for the radius equal to 0, you're going to recover the system that we want to study. But as you increase the radius of the hole of the indent, you're going to have some stuff weird. They are going to be a little bit mixed. So as you can see over here, these guys looks like they are like twisting. So you have something like a torsional mode, but it is not clear. So the question is, what is going to happen with the exceptional point when you add the gamma parameter, right? So it's going to happen something interesting. Let me show you. Again, this is the displacement. It's going to be always the same scale. The red is going to be the maximum displacement, and the blue is the zero displacement. So as you can see here, and as I told you, because we designed this system by hand, uh, it is very isolated. So it is going to be very difficult for the plate to promote, to excite the torsions of the pillars. Okay, so let me show you this image for the case where the radius is equal to 0. You are going to have just the two modes. So if you add the gain and the losses to the pillars and you start changing that parameter, you are going to have you're going to find the exceptional point. So it's going to be over here. So everything is normalized. So this is the real part of the frequency, and the imaginary part in red is going to be splitted exactly at the exceptional point position. But let me see what is happening with the simulations when I add the gamma parameter exactly at this position. So you're going to have these two guys, which are the torsional modes, and there's another guy which is trying to interfere with the shape of the exceptional point. I didn't say it. I forgot to say it. Um, the one way to know that you have an exceptional point is that it is a root square. So it both of the modes, both of the energies of the frequencies in this case are going to coalesce, but in a root square, square root. Okay, so here you can see it is quite obvious to see that there's an interference of the third mode with these two guys, but they also coalesce, and the imaginary part it splits. So in principle, it should be an exceptional point, but the presence of the third mode is going to be more complex to explain. I will take this part further. So you have here a simulation, a COMSOL simulation. Everything is perfect, but this is the case of loss and more loss case. Okay, so here you have for the symmetric case, I mean the gain and loss, you have the exceptional point, and in the case of loss and more loss, you are going to have also an exceptional point. But this is very nice. This is very nice because this is a numeric system, so it is a simulation of the reality, right? So these are the dimensions of the system that we build it. And as I told you, the idea of have a very nice bridge between the theory and the experiment, it is not as simple as that. Actually, the bridge, it looks more like this bridge than the previous one. So here we go. So you have, first of all, you have to take a big chunk of aluminum, because we decide, because it's cheaper, the aluminum, you can do it of copper, of silver or gold or anything you want. But we chose aluminum because it's cheaper, it's cheap, and it is very easy to work with it in the workshop. So this is our the principal chunk. You take it to the workshop. Let me zoom a little bit, and you start working with this is a CNC, which is basically, this is a very nice machine, which basically can work as a drilling mill. So you start working with the system, with the chunk of aluminum, and this is taking just the shape of the two pillars. You have to take away part of the material over here at the middle, and you will see something like this. This is a very nice picture of how this was um, um, how they were working with this. And finally, you have your system finished. So it is very nice up to this point. It's very shiny, it's very perfect as possible, because is reality is not exactly 12.8 centimeters. You have an uncertainty always related with the precision of the machines. So you have to deal with all of this always in experiments. And so this is the system. This is the system under study. So what do we need to do now? We need to excite the system, and then to measure the reaction of the system, right? So in a very nice cartoon, basically this is the system under study. So I will use a network analyzer. I'm going to send a signal. The signal is going to go to a transformer and then to an exciter. The exciter is going to do its thing. I don't know what thing, but it's going to work, and it's going to excite all of the system. And then I'm going to recover the signal with the detector, take it back to the transformer, and again back to the network analyzer, so I can analyze all of the data. Very simple, right? So that was the idea. I really like this cartoon. I don't know why my boss didn't like it, so he pushed me a little bit to do a different a different a different a different cartoon, a different image for the paper. So let me do a zoom again. So here we have again the VNA, the vector network analyzer, is going to excite a signal. The signal is taken to a transformer. Is going to excite the system. For example, here the E's always are going to are the exciters, and the D's are going to be the detectors. Actually, this here I have the base exciter. Here I have the base detector, and here I have the also the exciters and the detectors on the pillars, right? So this is actually the actual system, uh, obviously the red one. And this is not this is not no more shining as it was when it was born. So I'm sorry about it. So if you excite, let me use this again. If you excite, this is where your problems start, because the question now is what system, what is the tool that you are going to use to excite your system? What are you going to use to detect? And a good question is where, because you can use a detector, but if you put it in the wrong position, you're not going to detect anything. So as you can see here, we have two different lines. The solid black line represent the response of the system when you excite in the base and you detect in the base. So as you can see here, you have two big peaks over here, two resonances of the system, right? And you have something very small around this frequency range. Actually, the range where you should see the torsions of the pillars. And as you can see, the torsions are not quite big as the resonances of the whole system. So we have to change the position where you excite and you detect, because the movement, the torsion, it decreases, the amplitude decreases so quickly, and as a function of the distance into the plate. So actually what we did was to go directly to mount the exciters and the detectors, piezoelectric transducers, to mount them directly on the pillars of the system. So here I have the blue and the red solid lines. They show the two different peaks, which are exactly the torsional ones. And the other guys, because you are exciting and detecting directly on the pillars, you are going to see that the height of the amplitude of the other guys, which are in the neighborhood, are going to be decreased, because again, you have a metal, you have an elastic system, which is going to make that the amplitude of the excitation is going to be decreased. So it is you can see here that the height of the transmittance, when you are exciting and detecting directly on the pillars, that is going to be very, very small when you are trying to excite the other modes in the neighborhood. Okay, so the first idea was to excite and detect on the base directly, but we have to leave that idea because the peaks are very, very small, as you can see here. So we move to excite and detect directly on the pillar. That's it. And again, you have here that this is the symmetric case, the symmetric. I'm sorry, I'm looking at a different screen. So here you have the symmetric um, mode, and the anti-symmetric mode is over here. So now the question is, now you have your system and you can ask, how are we going to generate the loss? And you have to ask before that, what is the nature of this oscillation? Because this is not an electronic system. This is not an optical system in optics or in quantum mechanics. So this is a system in the elastic regime. So what is the nature of your oscillation? So I can tell you that the nature of the oscillation is exactly the displacement. So is the motion. And in order to generate a loss, you have to stop that motion. So that's the key of that's the answer of this question. You have to diminish the motion of the torsion, right? So this is the part of the experiment, and you can use a fluid or something, I mean oil, but you have two different options to stop the motion of the pillar. But we, instead of that, we use a dove, but a scientific body, and this is a compound, a sealing compound used for vacuum chambers. So you know that we really like to play with different stuff, and we find for our delight that this worked very, very well, this little party. What I'm going to do with that party, you can try to put layers. For example, that's an idea that we started with that, to use layers and in around the pillar, but we found that it is not a very good idea to do that, because the only the a very small layer of just imagine that you add a big ball of putty and in the pillar, just the first layer, just a very small part of the ball is going to interact with the motion of the pillar, and all of the rest is not going to play any role. So you don't have to do that. So, and another idea was to do small balls of putty, and you can put it directly at the top of the pillar. Why at the top? Because the biggest motion, the biggest displacement of the pillar was exactly at the top of the pillar. So it is meaningless to add the putty at the base of the pillar, because the biggest motion, just remember that you have here your base, and you have here your motion, your pillar. So it is moving something like this, right? So at the base is very clamped because of the medium, and all of the motion is going to be just at the top of the pillar. So we add balls one by one. So I am showing you here three different cases where I have no balls, when I have 17 balls, and when I have 25 balls. So you start from the center, and you start adding the balls one by one and measuring every time. So you will promote the stopping of the motion of the pillar. And this is how it looks like in the reality. So here I have a configuration of, I don't know, 10 balls, for example. I started at the center, and I moved the I'm sorry again. So uh, so you started at the center of the pillar, and you add the different balls, you add the balls like in a spiral way. So you will, and you every time you add a ball, you're going to measure the response of the system when you are exciting and detecting directly at the with the piezoelectrics, and you will find something like this. Let me zoom this again, because here is very nice. So before I zoom it, so this is the amplitude in dBms as a function of the frequency, right? So I am just looking at the neighborhood of the torsional modes, and I'm going to add the balls to the system. So I will start with 0 balls, the solid black line. As you can see here, you have the two peaks of the two resonances of the torsional modes. So, and as a function, let's say let's see this case of 5 volts. You see now, you are able to see that now the peaks are becoming closer, and if you are increasing the number of volts, you will see, for example, when you have 15 volts, that it becomes just one single peak. So you reach you what you have made at this point is that you have your two different resonances, your two different eigenmodes, and they become one. So actually, when for the 15 volts case, we are already very far away from the exceptional point. So and a resonance as a function of the frequency, you can see that it has this shape, but this has a real and an imaginary part, and if you see these resonances in the arcane plane, you will see something like this. So as you can see here, for the case of no balls, you have the two different peaks are mapped as these two circles or something like this. It is not a perfect circle. That's the problem of the experiments. But the point is that you have something like this. So we perform a least square minimization for each time that we were adding balls to the system. For example, this case is for 5 balls, and you are seeing that the peaks are becoming closer and closer. So instead of have two circles, one in the top of the other, you have something like an amoeba at this point. And if you're keeping the process of adding balls, you will have one single resonance, and of course in the arcane plane you will have just one single circle. So if you plot all of the all of the all of the of resonances, all of the spectra as a function of this gamma parameter, you will see as here that you have the two peaks originally. This is the natural loss of the aluminum, so it is never become zero, because aluminum, everything, as you can see, it present losses. Losses are very important in physics. You can see that you have here the two peaks, and they are becoming closer, and they will reach each other, and they will become just one single mode, a super mode, and after beyond the exceptional points. And if you extract the position of the peaks each time that you are adding more losses to the system, you will have this, and this is actually the exceptional point. So the black dots are the COMSOL simulations, and the blue dots are our experiment results. So as it is quite obvious that here, that before the exceptional point, you will have the symmetric and the anti-symmetric the modes, coupled modes, and the imaginary part is something like this. But beyond uh, the exceptional point, the both eigenmodes are going to coalesce, as I told you. So they are going to become two supermodes, one in the top of the other. So they are going to be always, and you are breaking the PT symmetry, because if you add to this system, because actually this is how the system looks like when you pass the exceptional point, instead of have the symmetric and the anti-symmetric case, you will see that only one of the pillars is moving, and the other one is going to be static, or the opposite. Okay. And what else about this image? No, I don't. I guess that I said everything about this image. And of course, you are worried to prove that. Of course, you have a square root uh, coalescence of the experiments, and you just need to put them. Uh, so these are the experimental points, the black dots, while the blue and the red solid lines are, the red one is a perfect a square root, as you can see here, and this is our best fitting. I don't remember why is the A over here. It should be 1, but anyway. Um, so as you can see here, this is our best fitting, and it is around around a square root. So you can see here here the cursor, the pointer. I'm sorry. So this is another way to see that in fact you have a square root decay. So the red line is the perfect the square root, and the black dashed line is our best fitting. So the question up to this point, I guess that I proved you that we already found an exceptional point in an experimental way. So we are very happy for that. And the question is, because I told you before, what about the three modes scenario? Let me go back to the slide where I show you the three different modes, right? So we have the two modes, independent, very far away, very isolated, very nice. You add the gamma parameter, you will reach the exceptional point and everyone is happy. But what happens when a third mode is in the neighborhood and it is interfering a lot with the torsional modes? So it is going to happen something like this. So this is a simulation again, but we propose a system. We use the couple mode theory. This is another Hamiltonian, in order to try to give a phenomenological answer for this system. So as you can see here, I have again the case of the gain and loss system, so and also the coupling, but I will add also a different parameters. New in this case is the frequency the tuning of the third level near of the two torsional modes, while lambda 1 and lambda 2 are the interaction between the torsional modes and the third level. So if you start playing with these parameters, you are able to find something like this. Actually, this is our phenomenological model against the simulations. So of course, this is the case where you have a big hole in the middle, which is more complex than the. I mean, it's more complex than the system that we already studied, which is in some way more the simplest case, right? And let me conclude with this. So we developed the design of an apparatus which shows an exceptional point via numerical simulation, a theoretical model which describes phenomenologically the interaction of the three modes was developed, and we have created experimentally an exceptional point in the elastic domain. Let me acknowledge to the DARPA, which is the Defense Advanced Research Projects Agency, who funded this research, and thank you very much.
Okay, thank you very much, Victor, for this nice talk. And okay, so we open the session for questions or comments. And do we have questions from the audience? Thomas, yes.
Yeah, I wondered. I mean, I was somehow when you talked about these torsional modes, and I mean, in order to detect them, you can use an optical, say, device, mirrors and laser and things like that. Have you thought about it, or did you discard that from the beginning instead of measuring it with these piezoelectric things?
Right. Yeah. That's a very nice question. Let me tell you this, Thomas. We start this project from the scratch. So actually, this is the first experiment of this lab. So we started with zero, just with the VNA. So we didn't have a laser and a spectrometer or I guess this is an accelerometer, I guess, what you're thinking. In fact, it's a
No.
laser.
In fact, I just thought about the laser pointer and the laser and the diode, right? The photodiode.
Right. Yeah, that's correct. It is possible. In principle, it is possible to do that. But as I told you, we start from the scratch with this lab, and we didn't have too much resources. So that's why we didn't thought about it. And also, Fred Ellis had experience with these piezoelectrics, so it was more suitable to use the piezoelectrics because Fred knows them a lot instead of try a different thing. I don't know if that answered your question.
Yeah, right. I mean, can I have a second question? It's also about the experiment.
Sure.
Yeah.
So as I understood, you created this shape. I mean, the two square cylinders and the bottom plate. This was one homogeneous block, right? And you removed a lot of material. How important was that? I mean, couldn't you just say fix these quadratic cylinders, maybe with cola loca in the plate?
No. You cannot do that because if you glue the pillar, you are going to have an interface. So you're not so sure that it was an homogeneous layer of glue, for example, and after and also the motion of the coupling. I mean, if you have a bubble of glue in between the base and the pillar, is going to give you a bad measurement. So that's the first point. The second point is that you are going to deal also with an interface. So you will have a piece of aluminum, another piece of aluminum, and an interface of two interfaces actually, because you will have one of the glue in the middle of the two parts of aluminum is going to create a layer. So you will have a mismatch of the impedance of the system. So you are going to change a lot of parameters. So this is something that you don't want to do. You want to do a single piece system because it's, in principle, if everything is homogeneous and too many considerations that you have to think about, and you're not going to be crazy about it. You're going to trust the company of aluminum, right? But if you try to just paste and I mean, it will be very nice if you want to change the position of the pillars, but it's going to be a big mess. So I don't recommend that.
Okay, thanks.
Thanks to you.
Okay, more questions, comments? If not, I have one.
Okay.
One question. There are some instances in which you can some sort of see like chirality in the eigenfunctions of these exceptional points. Would this be too complicated in the system that you have? Like to deform the system and to go in the spectrum, to go around an exceptional point?
What do you mean with chirality?
It's because sometimes when you have, I think it's always, when you have an exceptional point,
Okay.
you can like to deform the system a little bit, and then to be very near in the neighborhood the exceptional point, and then you have your eigenfunctions here. And then if you go around this exceptional point, you will pick a phase, which is not going to be one, but perhaps something else. And these people have associated the stuff with chirality, because you pick a phase when you do one turn around the exceptional point, you need perhaps another to recover that the phase equal to 1.
Okay. I guess that I am trying to. I guess that I understood the question. but there is something that I didn't. So what do you mean with to enclose the exceptional point, right? So what is the? Oh, I'm sorry about it. So my question for you is, what is the meaning of enclosing? What is the parameters that you are going to change? I mean, you can change, you can play with, for example, gamma, right? But what is the other parameters that you can? I mean,
Yeah,
in order
I
to
think it should
close,
be.
you have
Yeah,
to
it should be.
change two parameters, right?
Maybe it is the. I don't recall very exactly right now, but I think it should be the coupling, and in your case, should be maybe the distance between the two pillars, right?
So I cannot help you with that. I mean, just with the simulations, because in the reality, you cannot replace the position.
Yeah.
I mean, you have to change two parameters to enclose a point, right? So one vertical and one horizontal. So one of the things that you can change is the very kind of easy is the losses, right, through the party.
Okay.
But the other one, the other parameter, you have to change the position of the eigenenergies. So what can you do to change the position of the eigenenergy? So you can change, for example, the dimensions of the pillars, but you can change the dimensions just in one direction. You cannot add. You can remove material, but you cannot add material, right? Or you can change the position, so you can try to enclose the exceptional point, but it's also something that you can do experimentally in the reality. But simulations, we can talk about that. Actually, yeah, we can talk about simulations. This is very, very nice.
And I was just wondering, because people always talk about in the theory it's easy to do it, but I've never. I think Barbara did it with microwaves, but
okay.
But I'm not sure about your system. Okay, so we have another question for the audience. It says, does the molecular arrangement influence random versus ordered, or maybe use other materials as carbon structure, maybe?
Well, it could be. I mean, it is, in principle, it is possible, I guess. Can you repeat the question, please?
So maybe, Ken, are you in the room? Ken?
No, it's not here in my room.
The mic is not working. So the question says explicitly, does the molecular arrangement influence? And between parentheses, random versus ordered, and maybe use other materials as carbon structure.
I mean, the second part of the question, I understand. Yes, you can use another material. Probably, of course, the position of the torsional modes of the torsions of the torsional modes of the pillar are going to change with the density, the Young modulus, and the Poisson ratio. So if you change the material, you're going to change the position. But in principle, yes, you can change it. But the first part of the question, I didn't understand about the disorder and the molecular. So no, I'm sorry. I prefer to say nothing about that.
Okay. So I think we don't have more questions. So Thomas.
Let me ask something then about this chirality.
Okay.
Just yeah, well, I mean, one way to change, say, one way to have a second parameter would be to change the frequency, right, of the modes. So, and then there could be different possibilities. Say, put your system under strain or stress, or Of course, with the flexural modes, maybe it's more difficult. I don't know. But
yeah, but if you
there
change
could be some option, right?
Yeah, that's correct. That's correct. But if you change the stress, for example, you are changing the material. So the problem now is totally different. Instead of have aluminum, you have to do the same structure, but now, for example, in lead or silver or copper. So in order to change the stress, you have to change the material, right?
No, I think maybe if you put the material under stress, I mean, if you pull, say, the cylinder, doesn't that change this Young modulus also for the torsional?
If you pull a little bit.
Well, not a little bit. Maybe you have to pull a lot. I don't.
Okay. Yeah.
I'm not sure. It's a question. I imagine that it should be like this. Well, like a string on a guitar, right?
Right. You change the position. I don't know. I guess that the so you have to pull it, but at the same time you have to let it vibrate freely, right? So
well, it does torsional. It does a torsional motion, right? So you can, in principle, pull right from the center of your cylinder, and it may still be able to make this torsional movement.
which is correct in principle. Yes, in principle, yes, you can do that. But I don't know experimentally how easy could be to do that. I mean, to be honest, the most simple thing that you can do, that we can do, if you are interested, is that we can perform some simulations and change parameters. That is something.
You can do that with COMSOL, right? And then
I can do it. Yes, I can do it. Yeah.
Of course, I mean, another problem of this proposal from Adrian is that you need to maintain this mode vibrating while you are changing the parameters. So that may also be, if I understand it correctly.
If I understand that, what Adrian is telling me is that I have to do several simulations. So the exceptional point, I mean, this is the original exceptional point. So I have to move this second exceptional point of different configurations in order to enclose the system, right? And this is something that
Adrian should answer.
This is something that I can do. I work a little bit with diabolical points, exactly when you are enclosing. So you are changing two parameters. So you are enclosing the equilibrium point, right? So in principle, yes. If you want, we can keep talking.
Okay, so just last question. It's from Pablo. Says that can the exceptional points be reproduced in systems with gain and losses without going into the complex plane for the eigenvalues?
Can you repeat it, please?
Sure. It says, can the exceptional points be reproduced in systems with gain and losses without going into the complex plane for the eigenvalues?
I mean, one part of the exceptional point, beyond the exceptional point, they are going to split the imaginary part is going to be non-zero. So this is something that you cannot avoid. So in that sense, if I understood well, the answer is no. You cannot go further the exceptional point, because exactly at the exceptional point, the imaginary part is 0, 2, right? So it starts splitting after that point. So no, you cannot. If you want to go further, no, you cannot avoid that.
Okay, so I think we can't close the session, and thank you very much for joining us. And but that would be all. Thanks.
Thank you, Victor.
Thank you all.
Victor.